Okay, 2.7, day 2 of talking about transformations. I know the previous video had a lot of information in it in terms of just different rules for how to determine whether there are stretches and shrinks, whether there are shifts, whether they're happening vertically or horizontally. What I have in this yellow box here is kind of the nutshell of what you want to make sure that you kind of have committed to memory, and that is any changes to your parent equation that are happening on the outside are in some way going to impact the graph vertically, and any changes that are made on the inside of that parent equation, that is going to cause a horizontal change to your graph. Okay. Of course, we know the vertical changes when we nodded our head vertically, we said those changes tend to make sense, but the horizontal changes, if you shake your head horizontally, those ones don't actually make a lot of sense. For example, when you add a number on the inside, you might anticipate that would shift it to the right. It actually makes it go to the left. And when you multiply by, say, a fraction between 0 and 1 on the inside, you may think that would horizontally shrink it. It actually horizontally stretches it. So what we're going to do in example 1 is we're going to look at these problems in a little different way. You're going to be given graphs, and you're asked to write the equation of the transformed graph. Now, here's what I will tell you. You will never be expected to look at a graph and be able to distinguish to what degree any type of vertical or horizontal stretch or shrink has occurred. That is very difficult to decipher that by the naked eye. So for examples like these 4 here, there will only be shifts up, down, left, right, and a possible reflection either over the x-axis or over the y-axis. Okay, so what you want to make sure that you're paying attention to, first of all, is look at the shape of the graph. That will dictate which parent function you're working with. So as you look at example A, you can see that this graph clearly has that V shape. We know that that's common to absolute value functions. So when I write this, I'm definitely going to be writing this as my absolute value of x. But I notice that I know that typically the parent graph has the vertex sitting directly on the origin, and this one looks like it's been shifted down 4 units. So if I want to show a shift down 4 units, remember down would be a vertical change, so I need to go on the outside of those absolute value bars and simply subtract 4. Okay, if I were to do that, that would create this graph that we see pictured here. Okay, looking at example B and C, these are both parabolas. So now these are parent functions that are x squared. Kind of a similar idea here. Normally the parent parabola sits right at the origin at 0, 0. This one, though, looks like it's been shifted down, I believe, 3 units. Okay, so I'm going to write f of x equals x squared, and since this is just a vertical shift, I'm putting the -3 on the outside. Okay, now it gets a little bit more tricky when you look at example C, because this one has been shifted to the right 3 and then up 1 unit. Okay, in order to get from where it would have sat right here, it went right 3 and up 1. Okay, now when I write this, the up 1 is going to have a +1 all the way on the outside. But if I want to show going to the right 3 units, now I've got to make my parentheses a little bit bigger. I'm going to put my squared symbol on the outside of the parentheses, and on the inside, if I want to show going to the right 3, remember it's the opposite of what you'd think, you need to do a -3 on the inside. Okay, example D. Okay, a lot happening on this graph. It might be a little bit hard actually to see where that vertex is. I'm going to call it right here. It looks like it went, wow, these boxes are small. 1, 2, 3, oh my. 1, 2, 3, 4, maybe 5 to the right, and 1, 2, 3, 4, I'm like maybe 5 up. But then it also was flipped, because look at this parent graph I drew here. This got flipped across the x-axis in order for it to now be pointing down. So I need to show, we said right 5, up 5, and a flip over the x-axis. So up 5 would be +5 there. To the right 5 would be subtracting 5 on the inside, and a flip over the x-axis, that is when you multiply on the outside by a -1. So you want to make sure you put a -1 on the outside there. Okay, let's go ahead and we're just going to pick a few of these here in example 2 to kind of review from yesterday before we throw one more kind of complicated piece into this here. Okay, so let's start with example A. You can see there's only one thing happening here. In fact, there's a big difference between A and B. On A, the 2 is being multiplied on the inside. On B, the 2 is being multiplied on the outside. So if I'm inside, remember what we said up here, we said inside, those are horizontal changes. So I'm definitely going to call this horizontal, and when you're multiplying, these are your stretches or your shrinks. Okay, you really got to slow down when things happen on the inside because it's not what you maybe would think is happening. 2 is a number bigger than 1, and normally when you think of larger numbers, you might think that would stretch it and smaller numbers would shrink. But it's the opposite when you're doing the numbers on the inside. So if I'm multiplying on the inside by a number bigger than 1, that's actually going to cause a horizontal shrink. And remember, these shrink and stretch factors horizontally are always the reciprocal. So that's a shrink factor of 1/2, whereas a 2 multiplied on the outside actually is a stretch, but it's a vertical stretch, and the stretch factor is just 2. Okay, let's jump over here to D because there's lots of things happening on D. Again, what I typically like to do when there's multiple things happening in the equation is I like to tackle and write down all the things that are happening on the outside, because I know that those are all my vertical movements, and those are the easy ones because those are the ones that kind of make logical sense. And then I double back and I address all the things on the inside. Those are the horizontals. So I'm going to tackle this -1 out here first. Okay, I'm going to say that that is down 1 unit. Okay, the other thing you want to be careful of is you see this -3 here? There are really 2 transformations happening with that -3. Okay, you want to treat the 3 and the -1 as 2 separate things. So it's almost like this. On the outside, we were multiplying by a -1 and we were multiplying by a +3. Now, we would never write it like that separately, but that's really what happened, okay? Multiplying by a -1, that's what causes your reflections, okay? You should never say that you're having a vertical stretch or a vertical shrink and then say that the shrink or stretch factor is a negative factor, okay? Those are always positives. So that 3, I'm viewing it as a +3, and I'm calling it a vertical stretch, and my stretch factor is going to be 3. Okay, now the -1, I'm going to call that a reflection or a flip over the x-axis. Okay, now on the inside, I'm multiplying by a fraction between 0 and 1, so I'm going to call that actually a horizontal stretch, and my stretch factor is the reciprocal of 1/8, it's 8. Okay. All right, it's just going to take some practice to kind of get the hang of this here, but I do have one more piece here that we need to talk about here, okay? And this is the element. It doesn't happen in every single problem, but you have to watch out for this specific case. When you have 2 transformations that are occurring at the same time on the inside of your function, okay, and one of those transformations is like a shift horizontally, like either adding or subtracting something on the inside, you have to factor out the lead coefficient on the x in order to tell what the true horizontal shift is, okay? So in other words, the coefficient in front of your x has to be a +1 before you can identify how many units it's moving left or right, okay? I'll demonstrate this here with example A, okay? Can we tell that as you look at example A, clearly on the inside of the absolute value bars, there are 2 different transformations happening. I'm multiplying the x by 8. It also looks like I'm adding 5 on the inside. Okay, here's what I would encourage you to do. Write down all the transformations on the outside. So we're going to write down that we're shifting down 2 units. Go ahead and write down your horizontal shrink of 1/8. Okay, the shrink factor is 1/8, and I'm getting that from that 8 there. But you need to save the description of how many units it's moving left or right until you have factored out the lead coefficient of the x. Okay, so in other words, you're going to take that 8 that's in front of the x. We need the coefficient in front of the x to be a positive 1. Now, when I say to factor it out, the 8 is not going to jump outside of the absolute value bars. It is still inside the absolute value bars. But remember, when you factor, what you're really doing when you factor out something is you're dividing each term by what you're factoring out. So you're going to take the 8x, you're going to divide it by 8. That will tell you you should leave a x there. And then you're going to take the 5 and divide it by 8, and that would leave the fraction 5/8 there. Okay, I'm going to highlight this. This is what you would, I want to make sure you can see this here. This is what you would look at when you go to write down how many units did this actually move left or right. So because there's a plus 5/8, once I have made the number in front of the x a positive 1, I'm going to say this is going to the left 5/8 of a unit. So it's going to the left a little bit more than half of a unit. If you were to graph this original function right here on your calculator, it would not look like the absolute value graph went to the left 5. It would look like it only went to the left a little bit more than half of a unit. Okay, so this is only the case when there's two transformations happening at the exact same time inside the function, and one of them is some type of horizontal shift. Okay, so let's go ahead and try another one here. We're going to do a few of these so we can kind of get the hang of it. I'm going to write down everything happening on the outside. I can see I'm multiplying by 4 on the outside. I should call that a vertical stretch. I'm going to say the stretch factor is 4. Okay, I'm also going to write down what this 2 is. That is a horizontal shrink. The shrink factor is 1/2. Okay, I'm saving for the very, very end my description for how many units this actually moved left or right. Okay, so what I need to do is I need to take whatever the lead coefficient is on the x at the beginning of the problem, and I need to pull that 2, factor it out of this 2x and of that minus 1. Okay, so if I factor the 2 out, that gives me my x that I was wanting, but then it leaves behind the fraction negative 1/2. Okay, I'm going to highlight that. That negative 1/2 is me saying, oh, this graph actually went to the right 1/2 of a unit. Okay. All right, let's try example C. Okay, in example C, I'm going to do all the outside stuff first. I see a 1/3 on the outside. I'm going to call that a vertical shrink. The shrink factor is going to be 1/3. This 3 that's all the way out here on the outside, I'm going to call that up 3 units. Okay, then I'm going to address the stuff right in front of the x. Remember the other problem we did where we had a 3 that was negative? This 2 being negative, this has 2 transformations packaged into it. Think of the 2 as being positive, and there's also a negative 1 that's multiplied on the inside. So I've got 2 horizontal transformations from just this piece right here. Okay, a positive 2 on the inside would be a horizontal shrink. The shrink factor would be 1/2. A negative 1 on the inside is a flip over the y-axis. Okay. Now I have one last thing to write down for this, but it's not going to be going to the left 4 units. Okay. This is where I now am going to take this problem. Okay. Anything that was on the outside stays on the outside, but I'm going to take my lead coefficient of a negative 2. And I'm going to divide each of the terms inside here by a negative 2, and that gives me a positive x, but look at what this part becomes. A 4 divided by a negative 2, that's going to be a negative 2. So I'm going to highlight that, and that's going to tell me, oh, this is actually going to the right 2 units. Okay, to the right 2 units. Okay, let's try example E as our last one here. Okay, example E. Okay, I'm doing all the outside stuff first. So the 7 would be a vertical stretch factor of 7. The -2 would be down 2 units. The 1/5 on the inside would be a horizontal stretch factor of 5. Okay. By the way, they shifted here from the absolute value being the parent graph. This is now, it's a little harder to see, but see this exponent right here, the squared? That means the parent graph is just x squared. This is a parabola. And so anything inside these parentheses, that's on the inside of the function. Okay. Now, I don't just want to say write 10, because that's not actually true. I cannot say write 10 until this number in front of this x is a positive 1. Okay, so be a little careful with this. Keep the 7 there. I like to upgrade the parentheses into a set of brackets because I'm going to factor the 1/5 out. And I'm going to I'm almost going to have like double parentheses in this problem here. Okay, I'm going to divide that by 1/5. And now I'm going to divide the 10 by 1/5. Okay, now if you take a -10 and you divide it by a 1/5, that's the same thing as multiplying by the reciprocal of 1/5. That's going to make this number in here -50. Okay? So technically, this graph is going to the right 50 units. Okay? 50 units. So I would encourage you, when you start the worksheet tonight, to go through and look at all the problems. I think there's close to 5 problems that have this situation happening, where there are 2 transformations occurring simultaneously on the inside of the function, and it will require you to factor. I would go through, pick out all those, and circle any of those problems on the worksheet so that you remember you have this extra step of needing to factor before you reveal the true horizontal shift. Okay? The other thing I just want to mention to you is, and I think we've worked a lot with the parent function being absolute value bars. We've worked a lot with this parent function. The square root of x can also be a parent function. So don't be tripped up if you see a square root of x in your problem. You know, you would interpret this 2 as being on the outside. That's a vertical stretch factor 2. You would interpret that 3, and there's only one thing happening, so I don't have to do any factoring here, as a movement to the left 3 units. Okay, so they can switch up the parent function on you. You're still using the same rules. Okay, also the other part to the back of these notes has us kind of go a different direction. Instead of giving you the equation and asking you to write down the description of all of the transformations, they are instead giving you a description of all of the transformations. They're telling you what parent function they want you to use, and then they want you to build how the equation would then look. Okay, so they could switch up the parent function on you. That's what I was saying back here, how they could just identify whatever parent function they want, and you would have to use that to build in the descriptions here. Okay, now here's what I would encourage you to do, and we'll just look at just a few of these here. As you're reading through these descriptions, I would maybe make note of whether it's going to be placed on the outside or the inside of the parent graph. So if it feels like it's a vertical description, okay, a vertical description. So this is a shift up 5 units. This is a vertical stretch of 3, and even a flip over the x-axis. That's when you're swinging it down or up over the x-axis. That's a vertical movement. All 3 of these, whoops, not inside. All 3 of these should be occurring on the outside of the parent graph. So when I build this, I'm only going to have the x in between the absolute value bars. Up 5 would be my +5. Vertical stretch would be a 3. And if it's flipped across the x-axis, well, then I'm going to make the 3 a negative. Okay, all right, let's try another one here. Here is a horizontal, remember compression just means shrink, so that needs to be somehow worked into the inside of the parent graph. Here's a vertical compression, that's outside, and then a shift down 6 units, that's also going to be outside. Okay, so I'm going to address the outside stuff first. I'll put my absolute value bars here. Okay, vertical compression of 1/2. Remember, if it's vertical stretches and shrinks, the number you see is the exact same number that you had in the equation. If they are horizontal shrinks or stretches, the number you see for the stretch or shrink factor, it has to be the reciprocal of that when you place it into the equation. Okay, we're going down 6, I'm going to put -6. And so if my shrink factor or compression factor is 1/2, then I actually in the equation need to put a 2 there. Okay. All right, let's do the next one here. A horizontal stretch of 3, that would be inside. Vertical compression of 1/6, that would be outside. Flip across the x-axis, that also would be outside. Okay, so outside I'm doing 1/6, and I'm going to make that negative because it's a flip across the x-axis. A horizontal stretch of 3, well, if it's a horizontal stretch factor of 3, what I need to be inserting into the problem is a 1/3, okay? Okay, let's look at just one more here. Let's take a look at this one. A horizontal stretch of 5 and a shift to the left 3 units. Now this is where it can get a little bit tricky. These are both inside, and this is what we were talking about in this lesson, how you have to be careful if you have 2 things happening on the inside and one of them is a shift. This is what most people would say. Please do not write this down. This would be incorrect, okay? To go on the inside and say left 3 would be a +3, and then a horizontal stretch factor of 5 would be a 1/5 x, okay? I don't know if you can tell what's wrong with that, but if you were given this equation to begin with, you would say horizontal stretch of 5, but you shouldn't be saying that this is left 3 because you'd have to factor out that 1/5. So here's all you have to do. Here's the only adjustment that you need to make is you just need to insert parentheses right here so that you're showing how this looks in its factored form. Okay, showing that 1/5 already factored out leaves you with this +3 here, which would indicate then going to the left 3 units. Okay. It also would be acceptable if anyone wrote as their answer with the 1/5 multiplied in there and showed that initially this would actually be a 3/5, which would change to a +3.